Okay, I'm gonna mute myself now. And
Can we see it?
yes, we can. We can
All
hear
right.
you, we can see you, you're in control.
All
Back
right.
to
My
you.
name is Larry Waters, and like Sean said, I've been in the heating and air conditioning business for 37 years. I went right out of high school into this trade. It's done me well. I've tried to stay ahead of the curve on technology, and coming up through that entire thing, we over the years installed a lot of systems that would make the lights dim when you turned them on. And so when we realized that we could install heating and cooling systems that could be completely offset with renewable energy, it became my quest to put those in as many houses as possible. And then, what do you know, a couple of years ago, they came out with a couple of names for it: electrification and decarbonization. And I had already been doing it for a while, so it's been helpful. So I'm from A-1 Guaranteed Heating and Air Conditioning in Vallejo. We're a 33 employee company. We have about 12 installation technicians and service technicians, and a primary focus of the company is electrification now. About 40% of the work is electrification. Let's start with why. Why Californians? Why is it important to electrify? And I think a lot of us on this call are probably in the know. We know this. Wasn't sure who the audience would be, but our quest for clean air is comprehensive. A 40% reduction in greenhouse gases by 2030 is an ambitious goal, and then being carbon neutral by 2045 is, it's a game changer. Utility costs are getting more expensive in California, and electrification opens the door for net zero. Building electrification does yield effective greenhouse gas mitigation, depending on who you talk to. I deal with customers in the field every day, so I deal with a lot of different personalities. Some are accepting of this, and others want to reject it at all costs. So virtually no cost operation when we match it with renewables, and it saves thousands of dollars in fuel over the life of the system. And if we look down at the little snippet I pulled off of some web page the other day, and it's showing 6,389 pounds of carbon into the atmosphere versus 4,722, but that says electric heat, so I really don't know what that means. I'm sure that's not the way we're doing it, and you'll understand why that is. We should be proud to live in the state that's trying to do the most for clean air and actually has the top 7 dirtiest cities in the country. There's a reason why we're doing this. This is part of my presentation to my customers, is to inform them. Most people think we're doing a pretty good job, and there's a real awakening. And electrification is a fairly cost-effective way of reducing this pollution. California's clean air laws, we spoke about this a second ago, but they really rule the day. Everything is going to be focused towards this. Sean was talking about some of the hot water stuff and multifamily, low income, but my basic audience is single family homeowners. A lot of them who call me looking for a new furnace and end up getting a heat pump instead. I'm sure everybody knows gas prices are set to rise nearly 20% this year. They approved that increase, a 15% increase over and above the average inflation rate, and that's a big driver in my communication to my customers. And E3 report from June to the California Energy Commission, they were talking post 2030, mixed fuel homes always have higher bills than all electric homes. That's a big driver. Primarily, comfort improvements start the process of electrification through us. Most of the customers I see, or I saw in the early days, were people calling and wanting a new furnace. And so an individual conversation with each customer. And, a lot of people converted over to heat pumps, understanding that gas is going to increase in cost as deliveries reduce. The cost of the therm is going to have to rise to cover the cost of the infrastructure. So a lot of people understand that, and they're willing to make the additional investment for a system that is more future-proofed. And we're in a good time for this because technology has taken over a lot of aspects of our life, and some people understand that. My competition doesn't understand that. I got a question. Have manufacturers woken up to the huge volume of heat pump systems needed? The gas equipment folks, they're suing the city of Berkeley over the gas ban. How can small city engage directly with manufacturers to get volume discounts for citywide installation programs? You know, the manufacturers, as far as I know, the ones we deal with are embracing it, and they're bringing more units to the warehouse. There is a shortage of research and development. Some of these systems are not what we would call as user-friendly as our standard Nest thermostat. They're working on those things to make them more acceptable to kind of the way we're used to having things. Small cities could engage. I would say if a small city, the best thing they can do is welcome it through their building department and encourage it with the contractors that try it, because we get a lot of pushback even now from cities with inspectors asking, why did we take out the gas? I've had inspectors recently tell a customer that we did the wrong thing by putting a heat pump water heater in their house, and I had to come out there, meet the inspector, explain to him, show him the charts, show him everything, and he accepted it. But that's where we're at on that. 20% of my clients do heat pump water heaters at the same time. That's a rough number. We were looking at the numbers the other day to try to pull some stuff together for this presentation. And we sell quite a few hybrid heat pump water heaters as standalone improvements. I was actually at a house yesterday, and the customer was complaining about his electric bill doubling. And it didn't even occur to me, because he had a gas furnace, that he might have an electric water heater. And we were looking through the basement for some air sealing opportunities, and I noticed he had a GE GeoSpring water heater, and it had the light flashing on it, and it said that the heat pump had failed. So we tried to restart it, and the heat pump wouldn't restart, and we found the reason why his electric bill doubled. So strangely enough, he wanted me to put in a tankless gas water heater. And I told him that there was no way I was going to do that, and we're going to install a new hybrid for him in a couple of days. Envelope improvements, insulation, and air sealing are all critical to this process. We need to make sure that we have a nice tight house to put these systems in if we want them to perform predictably and the way that we explain them to the customers. We have this picture that you see here with the 3 outdoor units. This was my biggest lesson so far in this quest of ours. I originally put a single outdoor unit with 3 zones, and it didn't work well, and we had to put these 3 individual units. That was very expensive for our company to fix that problem, but we did it because the customer was not happy. Okay, there we go. Not just electrification, but good electrification. This is something I've kind of coined as a lot of my competition. I keep an eye on what the competition's doing. When they heard the word heat pump, we started seeing a lot of heat pump air handlers with strip heat and an 8.5 HSPF heat pump installed outside, and the customers thought they were getting this electrification project, and ended up taking 6 spots in the breaker box. Good electrification means that we have to be thoughtful about our design, optimize circuit space, install the right equipment so it needs less space. These systems that we install typically only need 1 2-pole circuit breaker to run the entire system. Traditional heat pump technology needs up to 6 breaker spaces and 70 amps of circuit equivalents. And good electrification is thoughtful and well planned out. This is kind of an unfortunate fact. Every time somebody misses an opportunity to electrify a customer, they're pushing back the entire cause by a decade or longer. Every customer is not informed about electrification will ultimately buy another gas furnace, and that gas furnaces today last 15 to 20 years. And the homeowners that buy that gas furnace, they're not likely to electrify until it becomes unaffordable for them to operate that furnace. Opportunities are being missed every day because of uninformed, undereducated, commission-driven salespeople. Our industry has not embraced this whatsoever. Our industry is driven by what the salesperson in the field wants to sell and what they can install the quickest. And since the process of installing the systems is more technical, it's unlikely that high volume HVAC companies will ever offer the solution until the law requires it. How they work. This is a quick schematic. A heat pump is like a refrigerator that runs in reverse. Heat pumps don't use electricity to create heat. They use mechanical means to move heat. And therefore, they're quite a bit more efficient than anything that's going to directly use electricity or gas to create heat. I'm not sure exactly who my audience is here today, so I put these slides together to kind of cover the whole basis. I'm sure a lot of us understand this. If there's any questions about this, if you want to raise your hand, I'd be happy to explain. When do we see lower GWP refrigerants becoming available as the new norm in the US market? I see that some of this is available in the European market already. United States is kind of slow to adopt certain things. One of the main ones is CO2 that they're using like in the sand and water heaters. But those are really a sealed system. The pressure is very high. I would like to see some alternatives, but I haven't heard any feedback from the manufacturers on when that's going to happen. Traditional compressors in heat pumps or even air conditioning systems, and we probably all live in a house that's got an air conditioner if we're in that type of area, and we know the house warms up, the air conditioner cools down, shuts off, the house warms up, the air conditioner turns on, cools down, shuts off. This is a huge energy waste. Every time the compressor starts, not only does it take on a lot of wear and tear, but it also uses a ton of energy. And the house never gets tempered. In order for us to put a heat pump system in, we need to make sure that the house is going to be tempered. The system runs much longer. This is actually a real-world graph of a project that we did, so you can understand how these systems work. We primarily install only ducted mini-split systems in various configurations. We don't do too many wall-mounted systems. This is actually a monitoring system that we installed on a 2-zone house with 2 outdoor units. 2 sides of the house. One side was much tighter than the other side of the house. And we can see the red and the blue arrows are pointing to the supply air temperatures in each zone. And then my lines across the bottom, you can see in the explanation, sitting on the bedroom dresser, in the other bedroom dresser, on the thermostat, hanging in the middle of the room, on the kitchen countertop. We were really trying to get a good idea of how even the house would be. And you can see as we turned this on, it was in 2018 in March, and it was a little chilly out. So the less efficient side of the house, when I turned the monitoring system on, was running about 92 degrees supply air temperature. And you can see the lines at the bottom kind of coming up on each other. And the system since that slowed down to about 84 degrees, then 83 degrees, and finally kind of rested right at 85 degrees to maintain that exact 72-degree temperature at the bottom. The other side of the house, the more efficient side of the house, obviously was able to condition the home with a lot lower temperature. So this is the beauty of the inverter technology. Instead of turning on and off to accomplish this, this system was able to sense the temperature in the house, make the adjustments almost instantaneously, and really find the sweet spot and keep it. And as you know, that line right along the 85 and the 79 there, that is when that unit is in extremely efficient mode. I'll show you in another slide how that works. But instead of starting and stopping, it adjusts to the load. As the requirements change, the supplier temperature self-adjusts to accommodate. This method uses far less energy. Any questions? The right airflow is critical for proper air mixing. I will tell you, I stole some of these slides. Correct size ductwork, known CFM, and proper registers are critical to make these systems work. The way we do these is not like old school where we go big duct, big room, small duct, small room, which is still the way the majority of the contractors out there kind of operate. We do load by load or room by room load calculations. We get into that ductwork catalog and that supply register catalog and find the right size and design for the right throw and spread and noise coefficient. And we use single direction registers whenever possible. This gives us that dynamic stream of air, and that continuous stream of air works a lot better than a traditional three-way register at mixing the air because of the time that the airflow is moving. These systems, when you have them on, the air runs continuously to constantly mix the house. I've had customers tell me that it's womb-like comfort in the house, or there's absolutely no temperature differential from room to room. The question from Nick, can existing ductwork on a gas furnace home be reused in most conditions? Most conditions, no. Some conditions, yes. They have introduced new, what they call medium static systems that have the ability to blow air a little harder. But most of the time we're re-engineering these duct systems, and when we install them, we're putting the duct runs in the middle of the house, very short. We're trying to gain all the energy from the reduced duct lengths and deliver that to the house. Most furnaces that are installed currently have perimeter systems on them. We have ran into a few homes where they do have the registers closer to the doors blowing towards the outside wall. We have reused some of those duct systems with good success with medium static systems. This is a beautiful thing. Inverter systems self-adjust to other home improvements. So if we put an inverter system in based on a load calculation with your existing windows, say, because it's part of a long-term electrification project, that system's going to be sized for the less efficient windows. When you put in the new windows, because the system modulates, it finds where it needs to be. It gets its own set point. It becomes a smaller system as your house becomes a tighter shell. This has been really good in being able to use the heat pump as the first improvement. The question is, can I explain a little bit more what medium static fan coil is? Yeah, I'm going to go, there's some pictures in the next couple of slides that I can use to explain that. It seems like I'm missing a couple slides here. So the medium static air handlers, all of these units have an outdoor unit and an indoor unit. And the standard units have a very small motor that pushes a predictable amount of air through very optimized duct system. The medium static unit has a little bit of a larger fan and has the ability to push harder against the duct system, much more like a standard furnace would. We are a Fujitsu Elite dealer, so we use primarily the Fujitsu product. They have medium static ranging in sizes from 12,000 BTUs all the way up to 48,000 BTUs. So they've really kind of opened up the market for larger homes. The problem is these units all have to be installed horizontally, so it's not an easy take out your furnace and put in this new system. There is some reconstruction and reinvention that needs to be done. What do the customers say? One of my favorite ladies ever. I forgot it was on until I got my bill. These are going to make your electric bill go up. Fortunately, when you tell the utility company that you've switched to electric, they will give you a much larger basis level of the cheaper kilowatts, at least in the PG&E territory where we operate mostly. Mr. Downer in Vallejo, he had a 1,400 square foot house that was built right around the turn of the century. We ended up installing a system in in an alcove in his kitchen, all home runs. Later on, there's a picture of that I'll share with you. But his house costs $0 to operate now because he has also installed solar. Another customer, Ben B from Martinez. It works great. There were 3 guys here for 3 days. Couldn't figure out how we made any money. That was one of our earlier jobs. We probably didn't. It's so quiet, and now we not only have heat in the winter, they have an option for cooling in the summer. A lot of these customers were heat-only customers. They were calling me for a new furnace, and they decided to kind of take the plunge. These are considerably more expensive than a new furnace. They're considerably more expensive than a new furnace, especially because we have to put all the new ductwork in and everything. But the addition of air conditioning is pretty tantalizing for a lot of people that have never lived with it. We have a question, how critical... Oh, this is a great point. PG&E won't give you reduced all-electric rate if you're on TOU. That's right. That reduced electrical rate is only good if you are not currently using renewables. How critical is solar PV in making all-electric work economically? You know what? These systems will heat your house. In most of the cases that we've looked at, they will heat your house for about the same price that you were paying with an old furnace. So if you had a couple of $100 gas bill in the middle of winter with your old furnace, these systems are not going to cost more than that to operate. We've found, and I'll show you in later slides what we found as far as the energy usage. We're loving the way the house feels. Never had such an amazing heating system before. It's fantastic. I just got this in an email from one of my customers yesterday. She was a 1,400 square foot house in Oakland, California. We put a 24,000 BTU ducted mini under the house with medium static, all new ductwork. She had a floor furnace. So people with floor furnaces love these because people with floor furnaces really aren't that comfortable most of the time, comes to find out. Unless you stand right above it, and then it's really awesome. And this is a comment that I don't think everybody's ever made. And I say this because I drive one of these. What's the best application? So here's what we're talking about. This is a mini split system. We have the small outdoor unit. A lot of these units are about the same size as your wife's suitcase, depending on how many shoes she's going to take on vacation. We literally just went to Europe, and my wife's suitcase was bigger than one of these units. You can see that I have shown on the side how quiet these are. The indoor units are 32 decibels, and the outdoor units are 55 decibels. That is incredibly quiet. When we're looking at unitary equipment, like a unitary 10 HSPF heat pump unitary, those are going to be around 65 decibels. These are extremely quiet. We know when we install these and we start them up, we have to walk up to them to see if the fan is spinning to tell if they're running. We've done over 100 of these in the past 4 years, and I narrowed that number down last night because I couldn't verify that I was up to 200 yet, so I wanted to be accurate. But we've installed a lot of these systems all over the Bay Area and beyond. There's a lot of different ways to put these in. The small size adds to the flexibility. On the left here, you see a mounted unit in a vertical mount. Some of the systems can be installed vertically, like you see here on the left side of the screen. That's actually inside a bedroom closet. You can see the line set in the back there. There's another line set going up. There was an identical apartment above this, or excuse me, below this, that had the same exact setup in the downstairs apartment. But nice and easy to install that way. Walk up to it and work on it. But not all of the systems are able to be installed vertically like that. Just over, you see the unit that's in the attic space. You can kind of see the insulation behind it. If you look closely, you can see the damper valve inside the damper there. And inside of that is a bunch of white stuff. That's the sealant. We generally get 0% leakage on our duct systems with these systems. But you also see how straight those ducts are. Those are not metal ductwork covered with insulation. That is actually flexible ductwork that 25 feet comes in a 2-foot tall box, and it's like a giant accordion. I'm sure a lot of you have seen it. That stuff is really only effective if it's pulled all the way tight. And we can't even make turns in that ductwork without adding mechanical elbows for proper airflow. It's critical that we manage the static pressure on these systems, especially these smaller standard static models. The registers and the boots going down the wall, all that has to be calculated. And it's very difficult. The first handful of them were very difficult to design, and they took a long time to install. But now we really, just like anything else, we have it down to a science, and my guys can install them in about the same time we could put in a traditional system with all new ductwork. Down below that one, you see one that we do a lot of, especially in the older houses with very low roof. Time is not short. I'm probably running a little bit ahead, so I'm going to read this question. In my Los Altos home, we recently replaced a 2-stage train gas furnace, first stage 94,000 BTU, stage 2, with a Mitsubishi heat pump 66,000 BTU, no resistant backup. And generally love it, but on Thanksgiving it was 32 degrees, quite cold for our location, and the house didn't warm to 69 until noon. 8 defrost cycles. Can you guess if it's undersized or a duct problem? We used old ducts since they have low measured leakage. You know, duct leakage is only one of the criteria that you need to look at for ductwork. It's funny, but we know in the industry, there was a lot of ductwork that was installed in older houses, and the house was designed to only have heat. And once the ductwork was sealed up, the system didn't work as well because it increased the static pressure of the system and it lost performance. That was with traditional stuff. We have to be really careful about just sealing up old ductwork. We need to know what the airflow characteristics are of that ductwork and the delivery. My question for you would be, do you keep this system running? We had a couple of customers this year that had similar complaints, and we were able to find out that they were turning the system off at night, and they were kind of losing the tempering in the system, and the house got very cold. And these systems do have a hard time when the house is cold and the outside is cold. But if you keep the house warm, they have no problem keeping it warm, because that refrigerant gas is warm going back to the outdoor unit, and it doesn't need defrost cycle as often. These units are designed to run down to 5 degrees Fahrenheit. I have never seen one do that personally. I know that these couple of houses we had, when we told the customers to keep it on and keep the house at 66, the system worked fine. I've also had customers tell me that they were overheating in the morning on the next morning because they turned them off, and the unit automatically kind of went into what we call turbo mode. It started running really quickly. But it could be that I would suggest, it doesn't say how large your house is, but I would suggest really looking at the ductwork, looking at the efficiency of the ductwork as far as, is it buried in the attic? What's our R value? You know, what's the static pressure in the system, and are you leaving it on at night? These systems are best just left on. Do any companies make vertical indoor unit that slips in the wall space left by an abandoned wall heater? No, but I'll show you a picture coming up here of what we did in a similar house to that. And we do use the line set, or we do run the line sets through the old exhaust stacks quite often. Okay, another question. The old furnace was 2-stage, but the Mitsubishi is inverter based. Do we keep it running? Do we turn it down at night, have it turned off? I think I answered that question. Keep it running, turn it down a little bit if that's the way you like to sleep, but don't let the house lose its temper. Do you need dampers to balance the system, or could this be done by adjusting the diffuser grill in these short duct configurations? You always need dampers. Dampers and air balancing. So I'll show you in another slide exactly how we deal with that. We want to adjust the air pressure at the plenum so that the air can be diverted into the other ducts properly. If we just shut off a vent down below, we're still building pressure in that duct, and then you'll get a whistling effect. But you won't get the same effect of being able to balance that airflow out through the other ducts if you just turn off your vent. And if you turn off your vent also, you're changing the aspect of the envelope and bringing, you know, a cooler room in against the uninsulated inside walls, and that can also cause an issue. That really depends on how tight we're trying to get. Thanks for all the questions. I really appreciate it. Sometimes big houses need 2 systems or more. So we like doing these systems up to 30,000 BTUs on one system. Sometimes if they're going to be larger than that, we try to go with 2 to give a little bit more zonability. As you can see, here's several different yards here with multiple units in them. And they're really pretty sitting out there. I don't know, maybe it's because I'm a contractor and I'm kind of a mechanical guy, but I really love the way these things look on the side of the house. It just gives me a warm, fuzzy feeling. Smaller sizing means ultimate zone control too. So I've got several houses where the back half, the living area versus the family room, You caught me off guard with that one. Versus the family room, so they can turn it down at night, or maybe the husband and wife have different kind of areas of the house they hang out in, and just really want great zone control. But it's important to keep in mind that when we have these systems running continuously, we're using a lot less capacity and we're using a lot less airflow. So typically I'm taking out a 1,500 square foot house. It might have a 60 or 80,000 BTU furnace and a 3 or a 3.5 ton air conditioner, depending on how crazy the air conditioner guy was that sold them that system. I had a 3.5 ton in my 1,600 square foot house when I bought it. We're typically taking those out and tightening up the envelope and putting in a single 18,000 BTU system in the attic space to do the entire load. And I get a lot of pushback over that. And the question a minute ago was kind of pointing to that. But it's not always about sizing. We don't want these units to shut off. When it's hot or it's cold outside, I want them running continuously. The effect of this increased comfort is based on the fact that it always feels like the house is warming up or cooling off. You walk into a nice cool house on a summer day that feels like the air conditioner is on but it's not blowing on you, that house feels very comfortable and crisp. It's when the air conditioner shuts off and the house starts to heat up that your body starts sensing the temperature. Since these units run almost continuously, they mix the air thoroughly through the house, and it always feels like the system is on, but not like when it's on when you're burning up or freezing. There's another question. Your recommendation is to leave it running so the house doesn't get cold, but if the house is empty for a few weeks, I guess a smart thermostat would be required to preheat before return. Yeah, and if you're leaving for a few weeks, you should turn it off. I mean, let's be good stewards of our energy. If you're leaving for a day, I wouldn't adjust it at all, because once the house loses tempering, we're going to use a lot more energy getting it back to equilibrium. That's the reason why you would have either a neighbor that would go over there and turn it on and have a couple of beers at your house and watch TV for a while, or maybe the smarter thing would be a Wi-Fi thermostat. All of these brands do have Wi-Fi capable thermostats available, and we installed them on a lot of these systems. And kudos for you for taking a 2-week vacation. This is a small unit in an attic space. This is a 12,000 BTU ducted mini split, and you can tell by how close all the rafters are that that's a tight attic. And one of the things that you can see in this picture, if you're super observant, is right up in the right-hand side, that yellow pipe going through is the old track pipe for the furnace gas that we pulled out. And if you look left, there's a black line set there for the old air conditioner that we yanked out. We changed out the existing gas electric system with 2 of these, and this was before the insulation was blown in. And believe it or not, we blew insulation in all that. You can see the bare ceiling drywall in there. When we put one of these platforms in, depending on, we try to get enough height out of it that I can get R30 under the platform. But obviously this one you can see, because of the zero of the roof, there was very limited space. So we were only able to get an R19 bat under this platform. But they will come in and blow in and around this. They'll leave our catwalk open. It's limited area for serviceability, but we'll get in there and crown most of this ductwork with insulation as good as we can. This was pretty tight. Here's a little closer look at the drop ceiling application. There's a lot of houses out there that are like this. They're about 1,000, 1,200 square feet. They have a 2-on-12 pitch or a flat roof, but they have a nice high hallway. That bodes well for this type of system, because we can get super short ducts. You see the duct towards the back of this is literally only maybe 2.5 feet long. The longest duct in this house, I think, was maybe 10 feet long, all the way down to the front. This one, we use 2 return air grills next to each other and right below the air handler, one for service and one for actually, there's filters in both, but we can pull them down and get to it to service it. This is a great application for those houses where you just can't figure out how to get it done. And we've done this in some houses that have had the wall furnaces, because there's a lot of those houses, there's not a lot of attic space. Any questions? Looks like we got a couple. All right, shifting peak time of use rates encourage pre-cooling and then limiting system use from 5 to 8 p.m. Yeah, you know, my whole thing with these systems and peak rate and all of that is I'm putting up enough renewable to cover the net energy for the year. When we're doing renewables, we've figured out how much these use and how much it takes to offset them over a year's time. The thermostats on these units are not conducive to being able to shut them off for several hours in the middle of the day. I mean, the programming on these things, most of these are made in Asia still, so they're not as easy to program as some of the stuff we've come up with. And when we do use a standard smart thermostat on these units, we lose some of the flexibility with the modulation. Do we have an example of a heat pump that replaces a standing gas furnace in a basement for a 2-story house and you can reuse your ductwork? Yeah, we do. So I don't have that example here, but I can tell you that example exists. There is one company, and it happens to be our unitary equipment provider. They do make an option where we can use a typical, what we call an American air handler, with an interface kit and a mini split modulating outdoor unit. It gives us a lot better performance than any of the standard standalone unitary stuff. You want to make sure that the ductwork is sized properly for the upstairs load. That's a problem we find a lot, is that the trunk line going upstairs is not large enough to carry the capacity necessary for the cooling mostly. So we can do it, but we take a really, really in-depth survey. We kind of map out the existing duct system. We do a load calculation and we verify that that duct system can handle the load. But most of the time in the 2-story houses, I'll tell you what I do. I put a small unit in the attic and I put another unit downstairs, sometimes under the floor or sometimes concealed. And then we turn it into an ultimate 2-zone, and then you get amazing, amazing comfort out of that. The other thing we've done is taken the system and put it in the attic space and blown the air down so that we have the system up on the top to deal with the upstairs better. Do we have dampers in that drop ceiling application? Absolutely. Every one of our systems has dampers, and every one of them gets an air balance. I think you can see them on the back one back there. It's harder to see that one. They've got it draped around. Or it could be this duct that comes off the front here goes all the way to the front living room, and that one may have been an 8 and it needed the whole thing, so they didn't damper it. But every job gets a load calculation. Here again is that beautiful job up in the attic. I love showing this picture because it shows craftsmanship on such a high level. These flex ducts are pulled very tight so that we lose the ribbing inside. You can really see the, let me just make this a little bigger for you. You can see the damper inside that duct right there. But one thing to see is that the entire air handler, what you see in this big box is the air handler connected to the plenum, which is connected to the ductwork. The entire air handler and plenum is all wrapped in additional FSK insulation in the attic space. We do everything we can to pull every little bit of performance out of these systems. it's important, if you're going to have a job like this done, to engage a contractor that is going to do this right. It may work fine and feel like it works good if it's not done this way, but it's going to use more energy. All of these techniques that we use here are designed to save additional energy. We were taught how to do this by a couple of the smartest people in the industry. Maybe some of you know Rick Chitwood and Dan Perunco and Gavin. Those guys are kind of our mentors. They helped us understand this stuff. They helped us with our very first project. We loved how it worked, and we just started running with them. I think they were a little bit amazed when we checked back with them and told them how many we were installing. They, I think, do maybe 1 a month. We're doing 4 or 5 a month. So this is, okay. Do you have an example? Also, can you show us or tell us what kind of air filters these use? What kind of maintenance is required? So the air filters that we put in most of these, and this is a good slide to see this, these filter grills that you see on the bottom of here, this is a 20 by 30 inch filter grill. That's 600 square inches. 3 times 2 is 6. Yes. That's a very big grill. And the unit that you see here is only a 9,000 BTU, right? So we have a tremendous amount of surface area compared to the amount of air that we're drawing through this system. We generally just use a 2-inch MERV 8 filter on these, in these large grills, but we have installed April Air filtration units, like whole house filtration units on the units in the attic space. We just oversize them by 3 times. So if we're putting in an 18,000 BTU, I use a filter that's designed for a 5-ton traditional system so that I can really increase my surface area and reduce the drag. We've found that the static pressure drop on those is really minimal if we do the plenums right. So that's kind of my solution for that. We've also, for clean air, we've attached these ultraviolet light machines on these that they create this oxidation in the air. They're really cool. They're kind of all over the industry now. How about service access in a drop ceiling? Is access requirement so unlikely that you could just sheetrock the entire drop ceiling? No, Lawrence Dietmar asked that question. No, we do have to put access below this for ease of serviceability. These systems are extremely dependable. We have very little callback or service on them, but when we do, we need to have good access. So usually we put 2 of these large grills next to each other. So one of them is an access grill and one of them is doing more of the filtering, and we put 2 filters in each one of those. From conference, what is the turning process for all the dampers? Are they just multi-zone systems? Tuning process. I'll show. Well, so what we do is we do a room-by-room load calculation, which I think that slide's coming up. We do a room-by-room load calculation, and we calculate the necessary airflow for each room. We make sure that our return air pathways are unobstructed. And we send a guy up where the damper is, and we send another guy over by the flow blaster, and we use standard communication skills at a high volume, and we tune them out. Every one of them's a custom tune job. We try to get it within 10% of our load calculation. And why wouldn't you want a minimum MERV 13 air filter? It would be nice to have a really great filter like a MERV 13 in all of these, but unfortunately we really have to be mindful of the static pressure. And in order for us to use a filter with that type of arrestance, it would have to be massive. And we are using a massive filter like in this slide. Let me close this so you can see this slide. In this slide, this is a 9,000 BTU system. It's moving just over 300 CFM, and it has a 20 by 30 filter grill. probably most of your homes right now don't have a 20 by 30 filter grill. That's an amazing amount of surface area. On this one, we maybe could get away with a MERV 13, but since we're doing mostly retrofit, we have to do what works and where it works. When we're doing one of the units up in the attic and we're able to put the April Air whole house system on, those are MERV 13. So we try when we can do it. These units are kind of interesting. Okay, we got another question. Thank you for all the questions, because I think Sean gave me a whole hour and a half for this. Okay. What do costs run for furnace conversions where ductwork needs replacement, assuming 2,000 or less square foot? I actually go into this towards the end, so I'll talk about that in just a moment. These units can be concealed, and we can put these things anywhere. So we found this little alcove in this house. This was actually the first house we ever did. It's a 975 square foot house in Vallejo. It was built in 1944, right after the war. Very, very small, tight little 2-bedroom place. When I say tight, I don't mean airflow wise, because it was leaky as a sieve. Rick Chitwood actually helped us design this system. As a matter of fact, Rick Chitwood and the owner of A-1 Guaranteed are the ones that installed this system. All the ducts are inside the building envelope, so we were able to eliminate any kind of attic or what we call unfriendly attic influence on the duct system. The longest duct in this house is about 8 feet long. It's the one that you see going over the door. If you can picture it, in the doorway to the left of this picture where you see the little filter, that's a very long room, and it has an L shape to it. That room has an 8 by 8 supply register with an 8-inch duct, and you can sit in the kitchen nook, which is in the L shape of that room, and you can feel the air if you put your hand up high. The air movement in this house is amazing. So myself and several others at the company were helping with this project, wondering how it was going to turn out. We were doing a lot of envelope improvements were on the menu for this house, and we did this in the middle of winter when it was really cold outside. We wanted to see what it would do. So we put the system in, and we got it fired up, and we turned it on. There were still holes everywhere. None of the air sealing had been done, and the attic all the insulation was removed out of the attic. This house heated up pretty quickly. We were very surprised, but it got to an equilibrium in about 4 hours and was maintaining 69 degrees in the house with virtually no thermal work done yet. Now, one of A-1 Guaranteed's employees lives in this house, and he reports back that he keeps the house at 72 in the winter because his wife likes it warm, 72 in the summer. He has 8 solar panels on this house. He is nearly net zero in this entire house, except for we were pushed for time and space, and they ended up putting a tankless gas water heater in this house. This was 4 years ago, so please forgive us on that. This is a closer look at the one we were looking at a few minutes ago. The unit is installed in a master bedroom closet of an apartment. There's an apartment upstairs and downstairs. This is what it looks on the back side of that. There's a very large grill there. That grill is also a 20 by 30. There's your thermostat, and there's your single supply register for the whole family room and kitchen area. 850 square foot, 9,000 BTU ducted, 20 by 30 return air. Did 2 of these in 2 apartments right up above each other and put the 2 units on the roof. This entire project, I think, this was early on. This project, I think, was $17,000 for both of these systems for heating and cooling. The apartment owner had a quote for 2 2-ton package units, and they wanted to run ducts through the upstairs closet. So we saved him from that nightmare and got him away with 18,000 total BTUs for both apartments. Another question from Alice. Can you tell us more about what the April Air filtration or electronic filtration systems. I want to be sure the air quality is improved with the heat pump. Thanks. So the April Air is it's a readily available filter that we can get through the industry. It's a HEPA style air cleaner in the way that it's a passive media filter. It has a pleated surface area. So when you stretch it out, the one for the 5-ton furnace or the 24-inch wide model has 72 square feet of particle trapping surface area. So we have a lot of surface area. So it's very, very little airflow reduction through the system, about 0.2 static, which can mean a lot on these low static systems, but on the mediums, it's not as big a deal. And the electronic filtration system, what we use is this thing called the RIMI Halo, and it's a device that was it's supposedly NASA space technology. It was used in the space station, but it actively cleans the air using a oxidized oxygen molecule, and it'll actually help disinfect surfaces. It's really quite an amazing little product, and something you probably didn't realize, they're installed in every single airport across the entire world as a biological agent preventative. They also call that system the sneeze machine. So it's supposed to be able to cancel out all the germs in a sneeze before they reach the other person's face 3 feet away. I didn't really think about putting that stuff in here, but I would be happy if you wanted to reach out to me to give you all the information you need on that. This is, we were talking about this one a little bit ago. This is a unit, we found a little alcove off the kitchen. This is a 1930s Craftsman, 1,150 square foot alcove in the mudroom. We put an 18,000 BTU system in. We pulled a 60,000 BTU furnace and a 2.5-ton air conditioner off this house. That, strangely enough, didn't seem to heat it or cool it comfortably. We did add insulation to this attic space at R44. A couple of these ducts go through the adjacent bedroom and sidewall. 2 of them are actually going through the attic to the far bedroom, and those ducts were buried with insulation. We did some air sealing underneath the house around the plumbing penetrations to kind of stop some of the draftiness. This is the Downer house. He was the one that gave us the nice quote earlier. You can see it's critical, though, when we measure the width of these systems. That air handler right there you see is about 36 inches wide. It's about 7.5 inches deep and 24 inches tall. But we have to make considerations for the line set to connect. So you see there, as the line sets are turning into the thing, we need about 4 or 5 inches there. But can you see the nice custom plenum that we built to fit there to optimize the space? You can also see the damper handles in each one of those ducts, and it looks like they're all pointed straight up. So we must have been pretty good on our duct sizing. I took this picture a while after the system was installed when I went to go back and look at their hybrid water heater. This customer also opted for the hybrid water heater. We did have to go back on this one because his hybrid water heater was blowing cold air into the laundry room at a clip that he wasn't really happy with. So we ended up devising this cool little box that went on the exit that has a valve in it, so he can open up that valve and cool that little laundry room off in the summer, and he can shut that valve and blow that cold air out in the winter, and then it basically turns into a little exhaust fan for his laundry room. We'll see long term how that turns out, but it served the purpose. What's the process? And I think you guys were asking a little bit about this, and now the way the questions have lined out, I'm thinking I might have done these slides a little backwards, but what the heck, we're going to get the message out. We start with a real load calculation. On-site data collection, we use WriteSoft, Manual J, and Manual D to determine our duct sizes and our CFMs. We measure every room for airflow requirements and balancing. And those of you that aren't familiar with this, let me kind of explain to you what you're seeing. The top picture is the actual load calculation. This is a 1,500 square foot house in Fairfield, California. It had a 2.5 on 12 pitch roof. So we were really able to give it a nice spread of R49 insulation right down the middle, and it became less as it got closer to the edges of the roof. This system we installed on this one, if you'll look at the little red and blue gauges next to it, we took out a 3-ton system off of this house. The ductwork was squoze into the extremely hot uninsulated attic, and the air conditioner, it was reported, never really worked very well. We installed this system inside the building envelope, so all of the ductwork was kind of inside. We built a soffit across the hallway to get the ducts to the other side, dropped them into the closet, went sidewall into the 2 spare bedrooms you see there, did direct ducts to the master bedroom and the kitchen living room area. We have 1 duct providing 152 CFM that takes care of the entire living room and kitchen. And these ducts are up high, so you don't feel them blowing on you. You don't hear them blowing. These systems are extremely quiet because we're moving a lot less airflow through unobstructed ductwork. So most of the time they're nearly silent, although I've learned not to say silent to people because some people think silence is different than I do, having kids in my house my entire life. So you notice in the bottom picture here, we have 2 rooms of identical size, both 9 foot by 10 foot in the same construction house. One needs 48 CFM, the other one needs 31 CFM. And that's because we have the influence of 2 outside walls. And this goes contrary to almost what every other air conditioning contractor does. Air conditioning contractor duct sizing 101 is big room, big duct, little room, little duct. And it really kind of just ends there. It's super critical, since we've been doing this, to understand how much airflow a room needs. We're able to diagnose comfort problems in people's houses now because we have a really good understanding of airflow, probably better than a lot of the guys out there. And I was at a house the other day. The customer says, my upstairs is really bad. My master bedroom is very cold. The other rooms are very hot. The contractor was there before me, wanted to increase the size of the ductwork to the other rooms. But when we looked a little closer, he was just getting twice as much air as he needed in his master bedroom, and we're going to make an adjustment on that, and that'll even the whole thing out. So it's not necessarily that the hot rooms are not getting enough air. Sometimes it's the cold rooms are getting too much air, in the air conditioning side anyway. Any questions about that? Another critically important part of this process, to choose the right system size and design ducts for performance. So we have to choose the right system size based on the load calculation, the ducts sized for performance, but in order to deliver the air properly, we need to make sure that we have a predictable path for that airflow to follow. So what I want to do is I always want to put the register on the inside wall closest to the system and blow the air out towards the other side of the room. And that gives us a long flow of mixable air. And it reduces my amount of ductwork in the attic, and so I don't have those static pressure and attic ductwork energy loss. So I'm delivering that air into the room and letting it do what it needs to do with airflow instead of dropping it off where you think it needs to be. A lot of homes have all the ductwork over the windows, and those are called perimeter systems. They did a lot of those in the 60s and 70s because the windows weren't very good, and they'd blow that kind of, they'd wash the window with warm air is what they used to call it, to keep the windows from sweating. Well, we live in a different world now. To reuse an existing perimeter system is not a good process anymore. We found that we can save much more energy and make the house much more comfortable by eliminating that additional duct loss in the unconditioned space, which means attic or even the underfloor. So keeping the ducts as short as possible, making sure the registers are right, using the little table on there to find out if they're going to make noise and how much air they're going to put out for the size is critically important as well. The system, oh, that slide's a little big for this, I apologize. Okay, we're gonna go up here. Okay, the system, these units modulate. We've said the word modulate and self-adjust, and we've done all this, but this is really shows you how it works. This is an 18,000 BTU nominal cooling capacity system. This system has the ability to crank itself all the way up to 20,100 BTUs or slow itself all the way down to 3,100 BTUs. As you might imagine, these are using a lot less energy when they're closer to 31 than when they're closer to 20. When we're sizing these systems, we always try to size nominally smaller than, or excuse me, slightly smaller than nominal. So I want my system capacity, because remember, load calculations are looking at the hottest and coldest day of the year. All the other normal days, you don't need that much capacity. So if we're designing this system at nominal at peak, I know that on that hottest or coldest day of the year, with the extra little built-in capacity here, I've got plenty of capacity to take care of the issue. Most of the time, my system is going to be running somewhere between 20,000 and 3,100. Closer to 3,100, the better. That means the house is really at equilibrium. All the rooms are the same temperature. You're not hearing it operate. You're just feeling this womb-like comfort around you. It's an amazing feeling. The same 18,000 BTU, and this isn't the same with all systems. So Fujitsu is really, they've figured out the heating side on these. One of the other ones that we use, Mitsubishi, sometimes they're not as good on the heating side as they are on the cooling side. Their cooling overshoots and their heating has less performance. And a lot of this is going to depend on some of the other ratios we'll talk about in a second. But 21,600 nominal BTUs out of an 18,000 BTU system, and this unit will go all the way up to 25,600 BTUs if you need to. We call that difference between nominal and high turbo mode. And everybody that ever had a thermostat and a forced air system wished they had turbo mode when they came into the house and they ran that sucker up to 90 degrees to warm up the house fast. Or they turned it down to 50 degrees thinking that it was going to cool down quicker. These actually have that reserve capacity. So if you come into your house and you're sweating and it's 74 in the house and you want to kick it down to 72, it will actually speed up and give you more cooling or speed up and give you more heating. It's pretty amazing system. This is the most amazing part, is the energy consumption. It's crazy how little energy these things use. So this is an 18,000 BTU system. This is our most typically installed system. We are doing more of the medium static than this model now, but this is the one we have the most out there. And if you look at cooling capacity right here, if you look over to your left, across the dotted lines, there's cooling capacity, 1.5 kilowatts. So if you think about your wife's hair dryer, or some of us guys with nice hair, we might use the hair dryer too. That's about as much capacity as a hair dryer. And if you look below that at 1.67 kilowatts, that's a hair dryer on high speed. So we're able to heat a house for the same energy as using a hair dryer if we do it properly. If we put in a typical heat pump system and tell you it's going to be an electrification project and it pulls 45 amps when it gets cold outside, that's not good electrification. A system that I can put in that will make your house 100% comfortable all the time and uses the same amount of energy as a hairdryer, that is good electrification. The other part of this is I'm using one breaker space. So I have one 20 amp breaker that runs this entire unit. The outdoor unit provides the power to the indoor unit. I have no secondary circuit for that. It's just amazing. It's mind-blowing. This is what got us into this. This is why we were doing this before they had the word electrification was part of the vernacular. It's important to size up the envelope. Attic air leaks need to be taken care of. Insulation needs to be taken care of. We need to have a tight envelope for these systems to work. We're running them. We're heating and cooling your house with a system that's half the size of your existing one. It does run longer. It delivers the same amount of BTUs. It just does it over time. But we need to make sure Mother Nature can't work too hard against us. So we can size a heat pump to match any load, but for best results with a mini inverter heat pump, it's got to be installed in a good envelope. So we pay a lot of attention to that. We install a lot of fiber, whether it be paper fiber or fiberglass fiber. We install a lot of insulation. We bury almost all of our duct systems under at least R49 insulation. So we're getting on most of the ducts a couple inches of crown, but ultimate below and to both sides, you know, infinite R value. So we are really reserving the capacity by doing this process. Executing the install properly is critical as well. Line set assembly, refrigerant charge, and leakage. This is the doomsday part of this. These systems are notorious leakers if they're not put together right. The line sets that come with the pre-installed flares on them are not good. Many of the manufacturers say to get rid of the flare nuts and the flares that are on the pre-manufactured piping and put the flare nuts that come with them. We have a policy at our company. We only use the right type of flaring tool. We have one guy that's responsible for the flares on each project. He's the flare master. And we only use the bolts that come with the manufactured, the bolt caps, because those ones are much stronger. We have gotten our leakage rate down to, the industry standard for a while was 30%. We've gotten ours down to 3 leaks last year out of, so we're probably running 3 or 4%. So check and verify. Once these lines are put together, we put 600 pounds of nitrogen pressure in them and we let them sit for a half an hour. And then we evacuate them and pull them down into a vacuum only once we know that there's no leakage.
And,
Precise.
Larry,
Precise.
can I just ask a question quickly? Can you expand a little bit on more what a leak looks like, or how do you tell you have a leak?
Well, the way the leak manifests itself is in the call saying, you know, my system that you sold me for all this money isn't working today. And then basically when we come out to the system, a lot of these have safety controls in them that will shut them off if there's a loss of refrigerant. And when I'm talking about a leak, this is the refrigerant gas that's going through the system. It's what moves the heat through the system. And it's operating at a pretty decent pressure, especially in the heating mode. So the leak will manifest itself on the flare tools. So if you think about this as 3 components, we have the indoor unit that's either in the attic or in the wall or wherever we showed you those locations, and then the outdoor unit. Those units are connected with a set of tubes. In the old way, we used to, and you'll see a torch in that top picture, we used to braze everything together. These units, it's incredibly important to keep the inside of the piping clean. So we try not to ever braze them unless we're putting 2 line sets together. When you braze copper, it creates a little carbon effect on the inside that can travel through the system and plug up orifices. So the leak will manifest itself when that bolt doesn't tighten the flare nut down tight enough. And sometimes we'll see like an oily residue and it'll go, okay, that's obviously there's a leak there. Other times we have to go searching for it, and it can be a minute leak. We chased a leak on one system, redid our flares 4 or 5 times. We're out there a bunch of different times. Turned out it was a leak inside the air handler from the manufacturer. And it was a very slow leak. It would go like every summer we would need to go top it off. Fortunately, we do a 1-year turnaround maintenance program on most of these. So we're checking line temperature to verify charge. We never put the gauges on one of these systems unless we think there's a problem.
And I guess it's worth noting, you said that this shows up mostly in heating. And is that because of higher pressures?
Yeah, the pressures are much higher in the heating side. So we get most of the leak issues in the summer. And you know, it may be, we install a lot of these in kind of mild climate areas, so they're probably not getting used as much, a lot of them in the summer as they are in the winter. But the pressures are just higher with this stuff in the winter on that line set side. During the summer, the pressures are higher in the condenser, where all the kind of welds and everything are factory. But we're putting a lot more pressure in those lines during the winter time, so they're more apt to kind of, you know, spring a little leak around the flare there. Did that answer your question, Sean?
It did. This is the
Okay.
first conversation I've had with anyone about refrigerant leaks from HVAC systems, like on
Uh-huh.
the level. So I'm very attentive right now, going, oh, really? Oh, like that kind of thing.
Yeah, really. And well, this is primarily the reason why we can't do the CO2 in field installed applications, right? So we're talking here about pressures between 190 and 300 maybe. That CO2 operates under a pressure rating of around 1200 psi, right? So that's why with the sand and remote water heating systems, those are, they heat the water in the unit. There's nothing field serviceable in that thing because we just don't have the technology, the tools, or the expertise to do that. And some of the new less greenhouse gas
lower global warming potential.
Yeah, global warming potential. Perfect. Thank you for. But those gases, a lot of those are actually flammable now. So it's going to be interesting to see what they finally come out with, because it's going to change the protocols for sure of how we deal with that.
Yeah, and that 2023 is the likely year when the California is going to be banning these existing refrigerants. I hear that tons from Mitsubishi and Fujitsu and Daikin, these conversations with their trade reps, that they're trying to transition. And I don't know if you have any thoughts on that. You just said that the ones they might transition to would be more flammable. I think R32 is an example of a more flammable refrigerant that's lower global warming potential.
Yeah, I've only read a couple articles on that, so I am not the I'm certainly not the guy that would have all the information on that, but I'm wondering if they're going to phase it out kind of like they did the R22, where it's going to be phased out over time, where they'll just have manufacturers won't be able to ship and won't be able to service. But I mean, it's anybody's guess. I mean, California has been bold in their initiatives, so it's anybody's guess.
Okay, well,
but I haven't, I'm not privy to any information on that, so I can't really answer that question with any intelligence. And since I have limited intelligence, I try to keep it focused. I got a question here from Dittmer. What do you think about controlled dampers like Arizona to provide zoning? Example, concealed hallway unit serves 3 bedrooms, somebody goes to bed, mom works late, needs heat, or load calcs didn't account for different solar gain over the course of the day, and rooms would benefit from finer adjustment. We have had this issue where we balance the system in the wintertime, and then I get a call in the summer and says this room is a little off. So we've gone back, and then we kind of do a finer balance on the system. But the idea behind these units are, if you want to do dual zone control, like upstairs, downstairs, we want to use 2 systems and have the upstairs be a zone, the downstairs be a zone, both have their independent modulation available. But the idea of these systems is to have an extremely inexpensive way to heat your house that keeps the whole house even all the way through. It's less expensive to leave it running than to shut it off. And so when we get down to turning air off in this room or opening it in the other room, we really get to this place where we haven't defined a way to do that yet. We're still trying to get the whole house even. I guess that's the best way I can answer that. But because these systems are balanced, if we have a zone damper that shuts on one, it's going to throw the rest of the house off balance. So we haven't really considered that. We have talked about there being some sort of a summer-winter adjustment, but yeah, I don't know the answer to that, Alice. I apologize. On to the next slide here. What's the cost? Somebody asked this earlier. The value proposition. Most new heat pump systems, new ductwork versus a standard furnace AC box swap. So if a new heat pump system needs new ductwork, it adds cost versus somebody just coming in and putting a furnace and coil in, or doing a system without ductwork. Our prices on these systems are often comparable to a deluxe or premium traditional unitary system. I'm seeing contractors charge $15,000 to $22,000 for system replacements with a really fancy furnace and a really fancy air conditioner and a whole bunch of hocus pocus and a lot of, you know, the salesman stays in your house for 4 hours until you sign the contract, that sort of thing. A lot of that goes on in my industry. And we call those the buy low, sell high companies. They use off-brand stuff with a lot of features in it, and they sell it for just a mind-boggling amount of money. And they install those systems in a very short period of time, so they make a lot of profit on them. So the average high-volume, high-profit HVAC company sells deluxe systems without ductwork for 15 to 22 grand, depending on the features and how gullible the customer is, to be blunt about it. The smaller equipment is less expensive. These systems are generally less expensive than the unitary equivalent. Our average price is between 15, 5, and 20 grand to install one of these on a house. And a lot of them, if they're 18,000 BTU, I can also, and they're in a house that's around 1,500 square feet or less, after you get your incentive back, I can also insulate the attic and do some air sealing right around that $20,000 price point once you get your incentives back. You can see it's more profitable just to install furnace and AC swaps. They'll have less labor hours. There's no need for highly trained technicians. Making it zero. Great efficiency in very arid climates. I'm just going to go over a couple of these really fast. We're getting pressed for time here. Our data indicates that we've collected on I won't say several, a few systems. An 18,000 BTU unit in Oakland used 2,270 kilowatts per year. That was an 1,150 square foot house, 1,900 craftsmen. Located in better than average envelope ducts buried in R49 fiberglass. Fairfield, that little house I showed you on the load calculation, ducts inside the envelope. That's with, Fairfield gets warm. There's a lot of air conditioning going on there. So that's 2,330 kilowatts per year. He keeps that house 74 and 70. Solar calculated 6 panels for zero net comfort on these systems. So if we look at the amount of usage and the amount of offset average solar hours, it doesn't take much energy to offset these systems. They're not that expensive to operate. If you do the math, because the way we size them and the way we install them, they spend most of their time in that sweet spot between nominal and low output. They don't use that much energy. So there's not any reason why anybody wouldn't want to do this. I have customers that we put these in for, and these units are using less equivalent electricity cost than they were spending in gas to heat the house with the existing furnace. So, and we can get to zero with these, man. We put a bunch of these up with 6 or 8 solar panels and give you a zero net comfort system, and that's one of our packages. Adding hot water to the project. You went deeply into hot water. I'm just going to tell you a little bit of field stuff we've experienced, and here's a picture of one of the Rude units we installed. I like this picture because it shows kind of the size in comparison to the stack job washer and dryer. These things are quiet and efficient. We had to duct this one in and out because we didn't want to cause a pressure problem, and also, you know, we didn't want it to refrigerate that room out there. Question: training installers. We need to train people in heat pump installation, train more salespeople, tradespeople generally. Contractors struggling to get, you know, I'm going to have an exciting announcement about that sometime in the future. You're right. The training goes deep because ultimately the first person to talk to that customer is the person that's in my role in most companies, is the in-home salesperson. And we come in contact with the customer first. The customer is going to build a relationship with us. They're going to either go with what we recommend or what we don't. Believe it or not, I'm usually the only guy coming in with this, and it's yet another opinion. So training at the sales side is huge. But I'll tell you a secret. A lot of salespeople that are straight commission want to get paid really fast. And these jobs, you can't really install them the next day. So that's going to be, there's going to have to be a complete paradigm shift. We had a paradigm shift a number of years ago. And, you know, once you get enough jobs in the queue, it doesn't matter if you have another one for tomorrow. 80-gallon units on these things. You were talking about those before. We mostly install the 80-gallon units because they've got the best kind of reserve capacity. If you look at that, see that energy guide right there? $161 a year electricity cost for an 80-gallon water heater. if you look at the energy guide on a standard tank gas water heater now, it's like 262. These things are extremely efficient. This particular model has the super nice EcoNet, where it's like the Internet of Things. It will automatically do a firmware adjustment later. They're working on firmware that's supposed to work with demand response. We'll see how that goes. Setting expectations with the customer is critical. We've done about 24 of these out over the last couple of years. We've only had one complaint of noise, no complaints of lack of hot water. These things all in, including permit, are around $5,500 installed for an 80-gallon model. These are available in 15 and 30 amp. 15 amp units are great for stretching the existing electrical panel. It's common when we use air-to-air mini split to run a sub panel with one breaker. So we'll use one breaker out of the breaker box because again, good electrification. We want to be good stewards of the electrical panel. We use one breaker, we run it to a sub panel, and we run both appliances off that sub panel. We always set the unit at 140 and install a mixing valve at 120. I'm going to speed through these, Sean. I know I told you I wouldn't need 2 hours. The majority of heat pump unit only require a 20 amp breaker. Traditional heat pump systems can use 6 breaker spaces. We talked about that. That's not good electrification. This is what I see all the time. Customers tell me, well, the other guy offered me this hybrid system, which is a furnace with an 8.5 HSPF heat pump that's going to guzzle energy. It's going to use more energy in the few hours that it operates down to 40 degrees than mine will all winter. And they're going to put a furnace in there that's going to, we all know what's going to happen with gas prices as people adopt electrification. They're going to go through the roof. This is not a good deal. It should be against the law in California to sell those systems, in my opinion. Installing a heat pump with HSPF below 10 should be a misdemeanor. Most contractors use 14 SEER 8 HSPF guzzlers. Most competitors don't believe in what we're doing and commonly tell my customers it can't be done when the customers ask them questions about what we're doing. I don't think we need to say anything about this picture. This is not good electrification, right? It also has to look pretty. But, I was over in Italy recently, and I saw one of the most unique installations of a mini split ever. Look at that bad boy. We're just going to go ahead and cut a hole in the wall for the fan of the condenser and have the air handler right in the room with it. So that's a unique way of dealing with it.
Does that work?
I suppose it works enough. They're blowing. They're causing some pressure issues in the building. And this was a little shoe store. I think it was a bag store. You can kind of see the purse things in the window there. But yeah, they're blowing some cool air inside that room. They're sucking some air out all the time. But yeah,
okay.
That it's in Italy.
Right, which is sort of like the center of retrofit heat pump water, and heat pumps just generally.
Well, it's funny because we were going down through a toll booth area. I wish I would have put that picture on here. And there was, they had the split system water heaters out there with a water tank, and then the hoses going into the toll booth for a hydronic air handler. So they had these 3 pieces of equipment there, and I was trying to figure out why they did that and just didn't put a heat pump or put one of these in. But I'm sure it's because it was paid for with taxpayer dollars. But thank you for the opportunity to present what we call good electrification. It looks like we timed this exactly right. This is pretty cool.